So when you're looking at the following, what we're going to be looking at here is talking about the development of the atomic theory. When we're talking about the atomic theory, you have a couple different things to keep in mind. Timeline, but also implemented experiments that were very important to this development of this theory. So when you're looking at the following, we have Dalton was the first to come along in our timeline, developed the idea that atoms are indivisible particles. It means that the reactions are arrangement of atoms, and we talked about this kind of as the solid sphere model. After that, we know J.J. Thomson came along and he developed that there is some type of charge inside of the atom. Used that through the cathode ray tube, discovered that there's a presence of this negatively charged thing, which was then later identified or called the electron. Used the plum pudding model because of this. Plum pudding meaning that the entire atom was positively charged, made up of little chunks, negative chunks that were that of the electrons, which had a negative charge. The next thing to come along was the gold foil experiment, heavily talked about, especially from New York State, that we know the gold foil experiment was when Ernest Rutherford shot alpha particles at a thin sheet of gold, and through the gold foil, the alpha particles typically pass through. However, there were alpha particles that would bounce off or be reflected or deflected. Most of them went through, therefore we made the conclusion that atoms are mostly empty space. However, the ones that were deflected or reflected told us that there was somewhere in there some small, dense, positive piece in which we identified as the nucleus. Next model we came out of was the Bohr model, also known as the planetary model. Okay, we talked about the 7 rings. Each ring is a principal energy level that corresponds with a period on the periodic table. Each ring is again coordinated based off from what period you're in. If you're in period 1, you have only 1 principal energy level. If you're in period 6, it means you have 6 principal energy levels. Remember, lowest energy is closest to the nucleus. The farther you get away from there, the more energy that you gain. Because of your distance and proximity to the nucleus, you have to have more energy to stay connected. Last model that we developed was the wave mechanic model. Okay, that's the current model of thinking. Electrons exist in areas of probable location. We call these orbitals. They're arranged in sublevels. We know that we have the S, P, D, and F sublevels based off from where you are on the periodic table. And the last part about that is that we know electrons behave as probability. Okay, so we don't know exactly where they're going to be, but the darker the color, the higher the probability and the location of those electrons. Looking at the atom in general, some of the big pieces that we need to identify with that is, starting from the outside working in, we know that these are actually going to be our electrons. Okay, we know our electrons are found in those principal energy levels outside of the nucleus. We know that electrons are negatively charged and they have a mass that's so small that we count it as negligible or not count it. Inside of the nucleus, we know that we have protons. We know protons are positively charged. The easy way to remember that is the T in protons. So we know protons are positively charged. They're found inside of the nucleus, and we know that they have a mass of 1 AMU. We also know that the atomic number is actually telling you exactly how many protons you have in your element inside that atom. Next part that we have here is our neutrons. Neutrons, we know, are neutral. Okay, neutral. They have the same mass as a proton, 1 AMU, and we know that they're found inside the nucleus. If you ever need to find the number of neutrons, you can take the atomic mass and subtract your atomic number. That'll actually give you the number of neutrons that are found inside of your atom. We know that if you take the protons and the neutrons and you put them together, we know that they make up what's called the nucleus. Okay, so inside of the nucleus we have our protons and our neutrons, while we have orbiting around the outside, based off of the Bohr model, the electrons, even though we know that they're actually showing up in random probabilities based off from our density clouds. So some of the vocab that we're dealing with from this unit is the atomic number, which we know is the number of protons. That's the actual identity of the element. We have atomic mass, which is the weighted average of all naturally occurring isotopes. We have our mass number. Based off from our mass number, we have our mass number as our protons plus our neutrons. We have our isotopes, which we know isotopes is defined as the same element but with a different number of neutrons, so same thing, different mass. And we have our ions, which means that you have gained or lost electrons. So same exact atom, just with a charge, whether it's positive because you've lost electrons or negative because you've gained electrons. We also have ground versus excited state. Ground state, we know, is that electrons are in the lowest electron configuration. That's the same as the one found on the periodic table. However, excited state means that an electron has gained energy, thus moving away from the nucleus, being found on a farther out principal energy level. When we look at this, the big key idea that we're going to be talking about here is that the number of protons here, so our protons, gives the atom its identity. So we're just going to put ID. Okay, that ID piece there is what tells us exactly what it is. So each element has a unique number of protons. That's what gives it its specific identity. So when we're looking at the chart below, we need to fill in some of the missing information. So when we're looking at this, based off from having 11 protons, you can automatically identify who this is. So based off from this, we know that with 11 protons, we actually have the element of sodium. So when we're looking at sodium, we know that the symbol for sodium is that of Na. Okay? And we know that because it has 11 protons, and we found that on the periodic table. The next thing you need to do is figure out the mass. And so the mass of this, we know, is going to be our protons plus our neutrons, so 11 plus 12, which gives you 23. Last part you have to identify is an atom or an ion. Remember, ions mean that you have more or less electrons than you do protons. In this case, we have one less electron, thus giving us a positively charged ion. When you're looking at carbon, we have carbon 14. So carbon 14, and we know carbon always has 6 protons. So if we're filling this chart in, we know that this is indeed 6 protons. The electrons here, since it's not noted as an ion, we know that it's also going to have the same number, so that's a neutral charge. They cancel out. And our mass we have as our mass we have is 14, but we know that to find the number of neutrons, we take our mass, subtract our atomic number. Therefore, we have 14 minus 6, which gives you 8. Based off the symbol, we know that this is indeed an actual atom. Looking at the next one, I do not know the number of protons that I have. However, I know this is an atom, therefore I know that the number of protons is equal to the number of electrons, so I have 51. And then we look at our periodic table, and based off of having 51, we know that our symbol here is going to be SB. To be more specific with our symbols, you could put the atomic number in the bottom left-hand corner and the atomic mass in the upper left-hand corner. You're going to see that there are a couple different ways to write those based off of the symbols, so I'm just going to put in the letters for now. Next thing for question number 2, what I want you to do is look at the following and tell you which one is excited. So you're looking at the incorrect or a skipped fill order. So when we're looking at fill order, we know that it goes 1s2, 2s2, 2p6 is the maximum before we're going on. So we know that we have 2 electrons in our first principal energy level, and we have 7 in our second. No skipping here. If you look at choice B, you have 1s2, 2s2, 2p6, 3s1, which is in a correct fill order. So we have 2, 8, 1. When you're looking at C, you have 1s2, 2s2, 2p5, 3s1. Therefore, you can see that this principal energy level is not completely filled. The principal energy level of the second would only have 7 electrons instead of having 8. Therefore, C would be your excited state here. So this would be the one that you would choose. Looking at question 3. Question 3, we're looking at we want the atomic mass based off from the abundancy. So we're going to use our abundance, so mass times abundance plus mass times abundance plus mass times abundance divided by 100. There are a couple different ways you can write this. So our masses that we have is 28, 29, and 30, and we have 92.21%, 4.70%, and 3.09%. When you're looking at that, you can either divide it by 100 at the end, but I'm going to convert these straight into decimals. So I have 0.9221, and then I'm going to add that to my mass, so it's 29, and that's going to be times 0.0470 plus, and then my last mass, which is 30, and I'm going to multiply that by 0.0309. And if you were to solve that, you should get the answer of around 28.1088 AMU, which if you ask yourself, does this make sense? You have the largest proportion or percentage of your isotope being that of 28, therefore your answer does indeed make sense in that regard. As we move on, we're looking at some new key ideas here, and as we look at these new key ideas, we're looking at the key idea of spectral lines. So going back to that excited to ground, and we know that spectral lines are actually formed from the release of energy as an electron goes from the excited state back to that of the ground state. Each element has unique electron configurations, so each spectral line is unique to that of the element. So we use this as identification purposes. So to kind of illustrate that point, you see that we have the release of energy here. So you can see the electron falling back down a principal energy level, thus releasing that energy as a form of a photon, which we actually see based off from our eye. When we look at periodic table, just to remind you of the orbitals, not something that's always so heavy on the Regents exam, but something just for a good conceptual thought of chemistry. Remember that the S and P blocks are the same as the period. So if I have a certain period, so 1s, so there's principal energy level number 1, principal energy level number 2, 3, 4, 5, 6, and 7. And if you use this particular fill order, it makes it very straightforward to which sublevels you have actually filled. So we have 1s, the 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and so on and so forth. So again, I call it counting blocks. If you count the blocks, you'll have the correct sublevel notation every time, as long as you remember the specific sublevels in each principal energy level specifically. Last part here is talking about electron configurations, Bohr and sublevel, and draw the orbital diagrams for each of the following. So when we're looking at these different aspects here, we're looking at our electron configuration. So if we're looking at oxygen, you can actually get your electron configuration straight from your reference table. So we know that that's going to be 2-6. And since that's 2-6, we know that the first principal energy level, 1s and sublevel, always has 2 electrons. And remember, this is written as a superscript. And then we are going to end up with 2s2. And then you're going to end up with 2p4. So if you're counting across, looking back at this, we know that oxygen is going to be located right about here. So you're going to be 1s2, 2s2, 1, 2, and then 2p4. So 1, 2, 3, 4, putting you right where oxygen is located on the periodic table. Looking at a little bit more difficult example, we have chlorine, which we know is a 2-8-8 electron configuration. So looking at that, finding its location on the periodic table, we know that that is indeed going to be a 1s2, and then you're going to end up with a 2s2, and then you're going to end up with 2p6, so that completes the second principal energy level. So now moving into the third principal energy level, 3s2, and then we're going to end up with 3p6. So looking at that, we know that this is actually an ion, so we know that it picked up that extra electron, which is located right on the outermost principal energy level. So if we were to count this, we have 1s2, so we have our 2 electrons here. We have 2s2 and 2p6, so 6 and 2 gives you 8, which correlates to that 8. And then you have 3s2, 3p6, so 6 and 2 gives you 8. Remember, this is an ion. We know that non-metals form negative ions, therefore they pick up electrons. That's why this is 2-8-8, same exact electron configuration of argon. So again, looking at this, looking at the excitement and the unexcitement, so going from the excited state to the ground state, you can see that we produce different spectral lines. Nice part about that is it makes it easy to identify mixtures. If you're looking at the following example, looking to see which mixture, which 2 elements are present in the mixture, you must have all of the spectral lines. So if you're looking at A, we have the spectral line, this spectral line, and this spectral line. So we know that A is definitely present in our example. But let's check to see if there's any others. So if we're looking at B, we know the spectral line is present here. Both of these are present along with the remaining two. So we know that A and B are both present. Looking at C, we can tell that this first spectral line is not present in our mixture, so we know C is not present. And just to double check, that one is not, and that one is not anyway, so you have multiples that are not present. D, if you look at it, this one appears not to be present, along with this one and these ones as well. So we know that in this mixture, you have mixtures, you have elements of A and B. So again, using spectral lines to determine mixtures based off of the unexcitement of electrons.